It's been already 2 years since we got together as an investor of Nearfield. Since then, it's been great to see the progress that you and your team is making. They're really powering this whole AI economy.
That's right.
The whole semiconductor industry was only like $500 billion just a couple of years ago.
That's right.
And today we're talking about 1.5 trillion. And then now we're beginning to talk about 3 trillion by 2035. And the bigger the market, the bigger the impact we can make.
There are three trends in the industry that is happening. One is obviously shrinking further. We are observing the transitions to high NA, UV lithography. And that brings its own challenges in terms of resist metrology, in terms of the scanner productivity, stochastic nature of defects that is becoming significant. Second is on making architecture of the chips more complex. We observe now it's true 3D structures, switch to gate all around. And last but not least is stacking the chips to benefit from the third dimensions as well.
Right.
Advanced packaging comes with the trends towards hybrid bonding as well. So these are the three trends we see in the industry. And that is, in my opinion, the inflection point for the technology that we are bringing as a solutions.
Right. The world used to be flat. That's right. World used to be more two-dimensional. Now, with more demand for compute and more demand for the faster transistor, we are going three-dimensional, which makes traditional testing very difficult to do. Nearfield is here because it enables 2D to 3D transition much, let's say, easier path or helping that path possible. Is that a reasonable way to describe?
Absolutely. The way industry now look at the yield, which is very different than what used to be. Yield was the percentage of chips that works. If the performance was lower, especially for PC era, you could still use that chips, maybe lower performance. But if you look at the hyperscalers today, the data centers, the AI data centers, yield is defined not only by performance in terms of compute, but also with energy requirement, the power efficiency. Which if you scale it in this third dimension towards how many chips and what does it mean in terms of power efficiency or extra power that you need in these hyperscalers, data centers, it's significant.
And it's very complex integration of many things that are in there. It's not just one chip.
That's right.
And if you have a yield problems in the process, and if you cannot test it, this could be a real issue, right? For instance, when you look at NVIDIA Rubin modules, right? It is depend on where you buy it. It could be $40,000, it could be $50,000, or maybe $60,000. But it's very expensive.
Very.
And it's very complex integration of many things that are in there. It's not just one chip.
That's right. Indeed, AFM, atomic force microscopy, is being invented in 1986. And since then, it's been a very powerful instrument, mainly in research environment, in academia. Industry saw the opportunity to benefit from this tool, and that has been the transitions to also use it more into the semicon applications. But if you look at the architectures of the AFMs, it still is the same architecture, the core of how it was used in research. And that does not solve the challenges, the issues, the bottleneck that is required in semicon. Metrology, process control in semiconductor fab has to be stable. AFM, the traditional ones are not stable. They are sensitive and sensitive to everything because of the way the system is being designed. Next is that it works based on measuring atomic forces, but actually you do not measure atomic forces. You have observer signals that can be related to atomic forces. Now, why this becomes important is that you are blind. You feel something, it's like reading, you will be blind and then reading a texture. Now, traditionally, optical techniques have been used for detecting more 2D structure, like the example of the village that you gave. As we go more into the third dimensions, what is required is the ability to measure, to detect with angstrom level of precision and resolution. Today, few atoms misplacement has an impact in both frequency of the operation of the chip, but also the amount of minimum voltage you need to get the chip operational.
Right.
Which again at the scale becomes significant. Now, so measuring with such a high resolution. Second is the ability to measure often deep and very narrow structures. Again, if you look at the skyscrapers, often you have buildings that are raising very high. So you need to measure the full profile where it influences the performance.
Right.
So that comes on top of the resolution, the ability to measure these very narrow, very deep structures. Of course, non-destructively. And it has to be fast. It has to be so fast that it does not create a bottleneck in the process. Otherwise, you detect, but it's too late. The process continues.
Right.
But now, if you want to go inside such a complex structures to measure narrow, deep structures, you need a completely different architecture. And this has been what we developed back then in 2011, started with a clean piece of paper, taken a step back, what could be the architecture that solves these fundamental issues, being extremely stable and insensitive to disturbances that comes out of the chip itself. And that has been the reason that our solutions brings the requirements, the stringent requirements of semicon fabs being stable, repeatable, at high throughput, and be able to measure these complex devices. With the demand of AI and the extra complexity that it brings in the AI chips, process control, specifically within the domain of equipment, is becoming way more important. I believe we are building something, very impactful in the industry.